Well, we continue with our discussions today on gas liquid multiphase reactions and how they can be enhanced. So, therefore, in this respect I would like to tell you that gas liquid multiphase reactions over a solid catalyst, they can be significantly improved by the use of structured instead of fixed bed reactors. Now, this all of us know. We know that in fixed bed reactors, marginal improvements can be obtained by optimizing the catalyst size, the catalyst shape, gas and liquid distributors, catalyst loading method and flow regimes. So, people have tried this and they found that there is only marginal improvement in the reaction rate or in the conversion rate, because they do not fundamentally change the way the gas and liquid are reacting, or rather they do not fundamentally affect the way gas, liquid and the catalyst they contact each other. So, therefore, instead of fixed bed catalysts, people have then shifted to structured catalysts. Now, by structured catalysts, what we mean is that these catalysts, they are actually characterized with a straight flow channel and a flat catalyst surface, which represents, and this has represented a dramatic change over the conventional pellet catalyst, where randomness is very much prevalent. And these structured catalysts, they also have some other advantages not very relevant to multiphase flow. They provide bulk support and also they provide confinement to the two-phase flow. And they have been very successfully used in automotive catalyst converters, and they are very commonly termed as monolith catalysts or honeycomb shaped honeycomb reactors or monolith reactors. Now, in these particular reactors, what we have actually is, we have a honeycomb shaped structure where a large number of channels are drawn, and through these channels the reactants flow and reaction occurs, where the wall of the channel serves to be the catalyst, and therefore, the gas liquid reactions occur there. Now, these automotive catalyst converters, while they are very popular for gas phase catalyzed reactions, people have found that they could not be used with much success for gas liquid catalytic conversions. And the primary reason was because it was difficult to engineer the gas liquid flow morphology which would maximize conversion. So, naturally lot of work is being pursued, I should say, on how to increase the conversion in these particular monolith reactions for heterogeneous solid catalyzed reactions. In this respect, a good amount of work has been done, but relevant to our lecture is the study by Liu and Roy, where they have adopted 3 particular hydrogenation reactions. And in these 3 hydrogenation reactions, there is styrene hydrogenation, isooctane hydrogenation and toluene hydrogenation. Out of these, the first 2 are kinetically very fast, while the last one, it is kinetically slow. Also, we have seen that in the first 2 reactions, they obey, or rather they can very well be represented by the Langmuir type of kinetics equation, and therefore, if we can insert a dilute feed stream, the reaction kinetics, it can be approximated by a first order kinetic reaction. This was the reason for selecting these reactions. And what the researchers they did was, they performed these particular reactions in square as well as circular microchannels. Okay, it's not exactly micro, they had used a 2 millimeter and a 1 millimeter dimension, and they had studied 2 things. One was the influence of channel wall thickness, where they found that the channel wall, the thickness of the channel wall did not significantly influence the conversion, and the shape of the channel, because mostly in monolith reactors, since it is easier to make square or rectangular channels, so that was being preferred. So, they tried to see the influence of conduit shape on conversion, and this is the result which they have observed. They had used 2 particular catalyst, catalyst D and catalyst E as it is represented, and they have in this particular two graphs they have shown the conversion of olefin as well as the conversion of toluene. This is a fast reaction, this is a slow reaction, and it's interesting to see that firstly for both the cases we see that the conversion rate or the activity, it increases with linear velocity as expected. This happens for all the cases. Secondly, we find that the conversion rate is much higher for the case of a circular as compared to a square channel, and the increase or the enhancement in activity for olefin hydrogenation is about 2 to 3 times, whereas for toluene hydrogenation, which is a slow reaction, I would like to remind you, the increase in activity is about 3 to 5 times, which shows that circular channel enhances the apparent catalytic activity for reactions of both fast and slow kinetics over a range of flow conditions, not only at a few flow, but over a range of flow conditions by a few times. Well, after that, and the same thing has been shown by the mass transfer constant as well. In this particular case also we see that the mass transfer constant increases, and for all velocities, and definitely for the circular channel the mass transfer constant is much higher. Then people suspected that whether this activity enhancement was due to some particular difference in the catalyst material itself, whether if the way they were made, whether that was affecting the catalyst activity. So, in order to check it, what they did, firstly they tried to find whether it was really happening for both isooctane as well as toluene. So, what they did, they prepared, or rather they tried to just confine the reaction to toluene hydrogenation, for which they added small fractions of toluene into methyl cyclohexane in order to ensure that only toluene saturation was occurring, and then they performed the reaction in both a circular and a square conduit. For just toluene conversion, in the absence of any other reaction also the same thing happened, and the enhancement in reaction was, rather the circular channel was a much better reaction activity as compared to a square channel. Well, then they wanted to see whether really there is something to do with the catalyst material rather than the catalyst shape. So, for that what they did, they took the catalyst, they crushed the catalyst, they sieved it into 100 to 200 mesh of particles. So, therefore, when they crushed it, the shape factor is no longer there, and then they tested the activity in a trickle bed reactor configuration with silicon carbide as the diluent. So, therefore, here they were testing with circular and square monolith reactors, and in this case with the case of crushed catalysts. Now, when they tested the activity with the crushed catalyst, they found that in this case also the circular monolith reactor had a slightly increased activity as compared to the square monolith reactor, but the relative activity in this particular case was just 1.5. Whereas, when the shapes were retained, then in that case the increases activity was 2.7. So, therefore, from this it is very evident that the activity enhancement due to the channel shape, it far outweighs the differences that might exist in the catalyst material itself, and therefore, the differences which might exist due to catalyst impregnation, their physical properties, etc., etc., that does not affect the catalyst activity as much as the shape affects. And then they try to investigate that why such a situation occurs, and they found out that it primarily occurs because of the type of wetting or the wetting characteristics of a circular and a square channel. They found out that for proper reaction to occur, the surface needs to be covered completely by a liquid film and gas should be diffusing in this particular film. Only when gas and liquid, both the reactants are in contact with the catalyst, only then the reaction occurs and a faster rate of reaction occurs. Now, for the circular tube, we find that there is more uniform coverage of the catalyst surface by the liquid film, and there are no stagnant liquid phases, there are no sharp edges or corners where the liquid can get trapped and remain stationary. The gas cannot approach that region, and so those regions are not available for reaction. On the other hand, if you observe the square catalyst, what we find is that definitely in this particular case also, the square catalyst also, if you observe, it can be deemed as a morphologically smooth surface. Well, and it can also be enclosed, or rather it can also be layered, or it can also have a thin film on it. But due to the corner effects, if we find that although it is morphologically smooth, just like a circular passage, but it has a large number of stagnant or the dead zones which preferentially tend to trap the liquid, and these sites are not available for reaction. So, therefore, the catalyst activity, in order to get the enhanced conversion, it is not only important that it forms a very thin film and it ensures gas liquid reactions, but it is very important that both gas and liquid, they can approach the catalyst surface and the reaction can occur. Interestingly, the entire discussion which I had was for catalyst dimension of 2 millimeters. The circular conduits were of 2 millimeters diameter and the square conduit were of 2 millimeters edge. Now, when the catalyst size was reduced, or rather the conduit dimension was reduced to 1 millimeter, we found that definitely the reaction was enhanced. The catalyst activity was definitely enhanced. But the enhancement for the case of square conduit was much more as compared to the enhancement is the case of circular conduit. What does this explain? This explains that in a circular conduit, in the 2 millimeter case also, more or less it was ensuring efficient contact of gas and liquid with the catalyst surface. So, further reduction in dimension does not enable a larger amount of liquid gas solid contact. Whereas, for a square, the surface was inefficiently utilized in 2 millimeters, and a reduction in size guaranteed or enabled a better utilization of the catalyst surface and a greater enhancement in the rate. So, from this it was also concluded that suppose we keep on reducing the channel size till a point when the entire channel surface gets properly utilized. Now, after that, for further reduction in catalyst size will not bring about any further enhancement in the conversion of a reactant. So, therefore, the catalyst size, or rather the catalyst surface, it matters only to the extent till the catalyst surface cannot be fully utilized. Once fully utilized, the channel shape, it does not matter. But in this particular miniaturized systems, in this particular range, in the range in which the monolith reactors generally operate, the range between say 0.5 millimeters to 3 millimeters, this is the range where they generally operate. In this particular range, the channel shape definitely matters a lot, as per the studies which have been performed by Liu and Roy. Well, now we go to the next part of our discussion regarding the effect of inclination. Now, again I can show you a video in order to understand this particular influence. If if you observe once more, I'll start the video here. We have already seen this. Now with this particular bubble, if you observe this situation in an inclined tube, what do you find? You find that the bubble, in this case, it has shifted to the upper portion and the liquid is draining. There is a very thin liquid film on the upper portion, but the liquid is predominantly draining through the lower portion. And we find that in this particular case, if you observe minutely, if you compare the two videos, you find that the nose is slightly pointed in this particular case, and therefore the rise velocity is slightly higher in this particular case. Now, this is true for macro, micro, every system, and this is a very counterintuitive phenomena, because apparently what we think is that as in a vertical tube, the bubble should be rising fastest, and as we incline the tube, the bubble rise velocity should decrease. Why? Because as I have already mentioned, the bubble rises due to buoyancy. So naturally, as the buoyant effect starts decreasing, the bubble should also be rising at a slower and slower velocity till it attains the horizontal orientation and it does not rise at all. But we find a very counterintuitive phenomena in this particular case. We find that as we are inclining the tube, definitely the gravitational component decreases, but along with that, the nose of the bubble, that starts becoming more and more pointed. Since it becomes pointed, it can pierce through the liquid well and therefore it can rise faster. Further, we find that if we compare a vertical conduit and an inclined conduit, we find that the liquid film which falls in this particular case is axisymmetric. It forms a concentric annulus around the bubble. So therefore, there are greater areas of interfacial shear in this case, whereas the liquid in an inclined conduit predominantly falls through the lower surface. So naturally, the interfacial area or area of contact with the bubble is less, and as a result, it can flow much more unhindered while the bubble rises. Now, as we all know, the bubble rises by downward displacement of the liquid. So, the faster the liquid displaces downward, the faster the bubble will rise, right? And this particular opposing effect of gravity and channel shape is represented in the graph, which shows that with gravity, the rise velocity should decrease, or rather the gravitational effect decreases with inclination from vertical. The shape factor shows that the bubble keeps on becoming more and more pointed till some particular angle of inclination, and then of course it again becomes rounded when we make the tube completely horizontal. Due to this opposing effect, if the resultant velocity is plotted, we find that the velocity is not maximum in the vertical orientation, rather it is maximum at some intermediate angle of inclination which lies between say 40 to 55 degrees. So in this particular case, the bubble rise velocity is maximum. Well, there is another interesting thing which I would like to tell you. We had experimented, as I have said, both with gas liquid and liquid liquid systems. Now a gas Taylor bubble rises through a liquid for both mini as well as macro channels. But we find, as I have already mentioned, due to the increasing effect, or rather due to larger surface tension of the liquid, if we introduce a lighter liquid into a heavier liquid, it does not rise for large channels. It rises, it does not rise as a single elongated bubble in larger channels. Rather, it breaks into smaller bubbles, and then these bubbles, they start rising. As we decrease the tube diameter, the stability of Taylor bubble increases for the case of liquid Taylor bubbles rising through a heavier liquid, which we shall be terming as the secondary liquid. And this also explains the cause of the existence of slug flow in reduced dimensions for liquid-liquid systems, while liquid-liquid slug flow is absent for larger channels. This is just because Taylor bubbles are not stable in larger channels, and Taylor bubbles start becoming stable with miniaturization, which can be quantified by the bond number or the Yordwas number. Generally, it is said that for bond number less than 1, a liquid Taylor bubble can be formed. But at the same time, if we observe the liquid Taylor bubble, which we have done in one of our experiments which have been performed in the multiphase flow laboratory of the chemical engineering department, we find that the liquid Taylor bubbles, they exhibit some very interesting characteristics. Firstly, this experiment was done with a kerosene Taylor bubble rising through a water filled vertical tube. Just like air Taylor bubbles, it has a spherical nose, a cylindrical body and a flat tail. But we find, and also we find that the water flows as an annular film between the bubble and the wall. And the thickness of the film, it gradually increases from the nose tip. It keeps on increasing in the nose region and becomes steady in the tail region. These are similar for air and kerosene Taylor bubbles. But in this particular case, what we find is that beyond the bubble, there is a intense wake region which is formed because the downward falling water comes and meets the stationary water here, and as a result of the larger interfacial shear in this case, so therefore a large number of satellite bubbles, they are shed by the liquid Taylor bubble, and this particular wake region, it increases with increase in tube diameter, number one. And the other thing is that as we decrease the pipe diameter, we find that the wake region disappears. The other thing is, suppose instead of a kerosene bubble, we adopt a lubricating oil bubble, or the secondary liquid has a higher viscosity. In that case, we find that definitely the interface is wavy, but the wake region disappears under this particular condition. So therefore, we find for liquid Taylor bubbles, firstly they are formed only below a tube diameter. For our case of kerosene bubbles in water, we find that no stable Taylor bubbles are formed for tube diameters greater than 0.0461 meters. So therefore, the D critical for kerosene Taylor bubble from our experiments was 0.0461 meters. We also found that if the experiments were performed in a Perspex tube, then in that case we would need a much lower, we find that the Taylor bubble does not rise in this particular case for even for a much lower diameter or even for a much higher diameter. Okay, for the case of a Perspex tube, we find that the bubble, it does not rise, it just sticks to the wall, because we know in Perspex it is comparatively more hydrophobic as compared to glass. So therefore, the kerosene tends to stick and it does not rise for similar pipe diameters, and it will only rise for a higher pipe diameter. So the D critical is higher in that particular case. So therefore, the first thing is the main thing, or rather the characterizing feature of liquid Taylor bubbles is number one, the wake formation. We know that the wake formation, it increases with the length of the Taylor bubble. The larger the length, the greater is the interfacial shear. So more is the formation of this wake region. Secondly is the diameter. Higher the diameter, greater is the formation of the wake region. Thirdly, the viscosity of the secondary fluid, because more is the viscosity, lesser will be the wave formation. And finally, the interfacial tension. The higher the interfacial tension, more stable are the Taylor bubbles. And as a result, two heptanone bubbles rising in water are less stable as compared to kerosene or benzene bubbles. So, therefore, the wake formation in a summary, it depends on four things: diameter of tube, viscosity of secondary liquid, length of Taylor bubble formed, and interfacial tension. This has been observed, and here also we find another thing is the inclination. We find that as we incline the tube, the wake formation it decreases, because now in this particular case, as you observe, the shear is primarily on one particular side. So, therefore, it is less, the interfacial area is less, so wake formation is also less. But other than that, the effect of inclination is the same for an air as well as a liquid Taylor bubble. Well, the same thing has been reported even for rectangular, square and other symmetric conduits. But there is one thing which I would like to discuss in the next class is a special effect of channel orientation in rectangular conduits. So, thank you very much. We continue with this discussion in the next class.